Hello, wonderful physics students. I hope you all are doing well today. In the last video, we talked just a brief introduction to momentum, what it is, the units of momentum, and its formula. In this video, we're going to talk about something called the impulse-momentum connection. And after doing the first introductory page or so in the homework, we'll get right into impulse and how it relates to momentum. You'll have seen many of the stuff before when we talked about Newton's second law. So I'm just throwing that out there. We'll talk about how it's related in a little bit. So first thing I want to do is introduce the term impulse. So impulse causes a change in momentum. An impulse is a force acting for a given amount of time will cause a change in an object's momentum. So remember, momentum, we'll write it up here, momentum is equal to mass times velocity. So either I could change an object's mass or I could change its velocity to get a change in momentum. So do you all think it'd be easier to change an object's mass or its velocity? Well, probably the velocity. Yes, definitely the velocity. Unless, it's a train and it's just you trying to push the train, then it might be easier to put another sack of bricks on the train and change the train's mass to get its momentum to change. But in most cases, it's going to be easier to change the object's velocity. So let's look into this. So I got I got one better. Got a tennis ball. My dogs love tennis balls. I'll chase them for hours, but that's not the point of this video. We have a force acting for a given amount of time. So my hand, we will apply a force for a quick amount of time, and we'll see how this object's momentum changes. Boom, right? I applied a force for a given amount of time, and the velocity of that ball changed, right? So we all know from Newton's second law, right, an unbalanced force causes acceleration, right? And so this is just another way to look at Newton's second law. And you're like, probably, Mr. Matlock, why do we have to deal with more of Newton's second laws? Well, there's just certain applications in physics where it's easier to investigate momentum rather than look at Newton's second law, because the acceleration might be changing, the force is changing over time. And so this is just a little cleaner way to investigate some certain situations than if we were to just look at forces. So let's get into this and show you how it's related to Newton's second law, and really you've seen this before. So J is the symbol for impulse. J is the symbol for impulse. And impulse, the formula, is force multiplied by our change in time. So the force multiplied by the time the force is applied. Okay? And this impulse causes a change in momentum. So it causes the velocity, generally, to change of that object. All right? So let's dig into, and this is going to be our main formula for impulse-momentum connection. It's going to be force multiplied by our change in time equals mass multiplied by our change in velocity. This is our main formula. You all have seen this, and let me show you where you have seen this. So Newton's second law, remember? Force equals mass times acceleration, right? Well, what the heck is acceleration? Acceleration is our change in velocity divided by our change in time, right? So if I rewrite this, so force equals mass times our change in velocity divided by change in time. Now I go ahead and multiply both sides by our change in time, That cancels out, and we multiply our force by change in time, and we end up with the equation that we just showed above, right? And so this is just an application of Newton's second law, but we're just looking at it a little bit differently. And in the coming weeks, you'll see why this application is a little bit more useful than Newton's second law. So this is what I wanted to share, is just that force multiplied by time equals our mass of an object multiplied by our change in velocity. All right, so let's look at a little bit of a scenario. So here we have two cases, case A and B. And so for case A, we have a ball going towards a wall at 10 meters per second. And then afterwards, it hits the wall and bounces off, and it's moving this way at 5 meters per second. All right? In case B, we have a ball moving this way at 30 meters per second, and we have on the rebound, it's moving this way at 28 meters per second. My questions to you: which one has the greatest velocity change, the greatest acceleration, the greatest momentum change, and the greatest impulse? Well, let's dig into this. Why don't you go ahead and pause the video for just a minute or so and try and answer these questions for yourself. All right, so hopefully you've at least taken a guess at this, or an educated guess at least. If you said B, you are correct. Some people may think A, at least for velocity change, because 10 minus 5 is 5 versus 30 minus 28 is 2. Well, this one's bigger velocity change, is it? Well, what are our directions? In this one, afterwards, it's a negative 5 meters per second because it's going to the left, right? And here it's a positive. So if I wanted to do my delta V, is V final minus V initial, right? That's our change, is always final minus initial. We end up with negative 5 minus 10 equals a change of negative 15 meters per second. So we get negative 15. How about this one? We have minus 28 minus 30 meters per second equals minus 58 meters per second. I'd say this one has a heck of a lot more change in velocity than A. Well, so we have B here. How about the greatest acceleration? Well, we can assume that they take the same amount of time to hit the wall and bounce. It's a pretty short contact time. And so we have a much bigger, so remember, acceleration equals our change in velocity divided by change in time. If these are the same, our change in time, our velocity change is much bigger in B, therefore B is going to have a much bigger acceleration. So again, we have B. Well, who has the greatest momentum change? Didn't say anything about the ball changing its mass drastically during the collision. So again, our momentum change is whoever has the bigger change in velocity, which is B again. And what has the greatest impulse? Well, impulse is equal to change in momentum. So our greatest change in momentum will be equal to our greatest impulse. So again, it's B. So I do want to illustrate one more thing. let's say we have a car crash, right? And I think this is one of the biggest things that I want you all to come away from this unit with. And I'll share some other examples, but I have a car. And it's moving at, let's say, 30 meters per second, right? And then it hits a wall. And the car is crumpled. You know, there's a wheel. It's a crumpled mess of a car. And its velocity is 0. V final equals 0 meters per second. Well, if my change in velocity is equal to force my velocity change here is going to be negative 30 meters per second. 0 minus 30 equals minus 30 meters per second. The mass of this car is pretty much going to stay the same, right? The car isn't going to magically disappear half of it. It's going to be about the same. And this is what I want to illustrate. For the same change in momentum, if this side has to be minus 30, what happens if I have a big force? If I have a force of 30 or negative 30, what does my time have to be? My time is going to be 1, right? If I have a force of negative 30, I have a time of 1. Well, if I have a force of 1, my time is going to be 30. So this concept here, and I'm going to explain this a little bit more detail in the next video that I make and provide a few more examples, but if I have a big time, I have a little force. If I have a little time, I have a big force. And so we can greatly reduce injury by elongating the time of a particular collision. And I'm going to just go into a little bit more detail in this in the next video. So if that was confusing, stay tuned for the next video. I'm going to provide some real-world examples of this and help really further your understanding of this concept, because it's going to help you a lot in understanding the physics of car crashes, as well as the physics in your paper cars that you're building as well. Thanks y'all for watching, and we'll see you next time.